Hello, and welcome back to the channel. Today, we are diving deep into the Earth's architecture to explore a topic that is absolutely critical for finding the mineral and energy resources that power our modern world: structural controls on magmas, margins, and resource systems. If you're a geologist, an earth science student, or just someone who loves big diamonds and black gold, this one is for you. We often talk about the importance of geochemistry or geophysics in exploration, but structural geology is the unsung hero, the ultimate boss controlling where the treasure is actually hidden. Think of it this way: a chemical anomaly is like a note saying, "There might be soup here," but structural analysis tells you exactly where the big pot is waiting in the dark kitchen. In fact, if you go straight to drilling based only on a beautiful chemical anomaly, Mother Nature might just punish you with a dry hole.
Successful resource discovery is a highly collaborative effort, requiring the fusion of the exploration geologist's creativity and the structural geologist's meticulous quantification. The explorationist proposes the what and where based on regional models and conceptual thinking. The structural geologist then steps in to define the how much and how confined, providing the geometric and mechanical rigor needed to justify expensive steps like drilling. The most critical contribution of structural geology is defining the temporal constraint, identifying when structural events happened relative to the movement of mineralizing fluids. If a fault system developed after the valuable fluids were long gone, that structure is useless for resource accumulation, merely complicating extraction later on. If, however, the structure was actively deforming and opening up space during the fluid pulse, then you have found your golden ticket. Let's start with one of the most exciting resources: diamonds. Diamonds are delivered to the surface via a unique type of volcanic rock called kimberlites, which are the deepest mantle-derived melts ever to reach the Earth's surface, sometimes sourced from depths of up to 300 kilometers. This makes kimberlites unique probes of the convective mantle. The emplacement of kimberlite magmas relies entirely on deep-seated crustal structures, the Earth's plumbing system, to provide rapid, safe transit through the thick, cold lithosphere. Their distribution is controlled by ancient translithospheric structures, suggesting that deep-rooted faults govern the fluid flow pathways associated with these deep-seated minerals. In places like the Vajrakar kimberlite field in India, kimberlite pipes preferentially concentrate along shallow geological features such as granite structures and fault shear zones that extend 3-4 kilometers deep. This structural control is so strong that understanding the timing and geometry of these deep faults is essential for predicting complex pipe geometry at depth. When exploring for diamonds, you must interpret deep geophysical anomalies relative to the regional stress field to pinpoint where these structures created pathways for the kimberlite magma to ascend. Just finding a gravity anomaly is not enough. You need the geological skeleton, the structure, to explain how the deep diamond-carrying magma could burst through to the surface.
Moving from the deep mantle to hydrothermal systems, the structural control shifts from being a passive container to an active channel and localizer of valuable metals. We are talking about major economic systems, such as Cobalt-Copper-Gold deposits in metasedimentary rocks, like those found in the Blackbird District, Idaho, USA, and the Kuusamo Belt, Finland. These polymetallic deposits are typically structurally controlled, often clustering along major shear zones, folds, and breccia zones associated with deep crestal discontinuities. The geology of the host rocks is varied, often involving thick successions of siliciclastic metasedimentary rocks deposited in rift-type marine basins, which later underwent compression and metamorphism. For example, The deposits in the Idaho Cobalt Belt are hosted in Mesoproterozoic Metesidae rocks formed in an extensional basin setting, which were later subjected to our continent collisional orogeny, leading to structural localization. The critical concept here is the creation of dilatant zones, which are areas where the rock pulls apart under stress. Creating open spaces for mineralizing fluids to rush into. These dilatant zones, along with brecciation and fracturing within the fault network, act as the primary fluid conduits where metals like cobalt, copper, and gold precipitate. Therefore, successful exploration requires mapping these high-strain zones to accurately predict the geometry and plunge of the erebity for resource estimation. Interestingly, these COCUO deposits show potential links to the vast Iron Oxide Copper-Gold systems, or IOCG deposits. While most IOCG deposits are copper and gold-rich, but cobalt-poor, the metasedimentary-hosted COCUO systems, which are cobalt-rich, might represent a related style of mineralization. The search continues to constrain the characteristics of this possible affiliation, particularly regarding the sources of metals and fluids and the role of tectonism in their formation.
In the world of oil and gas, structural traps are the bread and butter of large-scale discovery, holding the majority of the world's hydrocarbon reserves. Here, structural geology plays two crucial roles, defining the initial trap closure and assessing the sealing capacity of the faults. In rifted lacustrine basins, like the Bahai Bay Basin in China, the overall development and formation are directly controlled by the activity of coeval major boundary faults. These fault zones, which initially look like simple lines on a map, are actually complex three-dimensional structures with discernible thickness, known as deformation bands. During tectonic movements, the stress along these fault planes leads to brittle fracturing and complex fault clusters. For a structural trap to hold oil or gas, the structural geologist must determine if a fault acts as a conduit allowing fluids to leak out, which is bad, or a barrier maintaining the seal, which is very good. Faulting fundamentally changes the petrophysical properties of the reservoir and seal rocks through processes like compaction, reducing porosity, or dilatancy, increasing permeability through fracturing. We need detailed structural geological modeling to accurately assess this sealing capacity and predict the preferential pathways for hydrocarbon migration.
2. How do we apply this structural rigor in a cost-effective way? The answer lies in lineament analysis combined with specialized structural modeling, a technique that drastically cuts down on exploration, risk, and costs. A lineament is essentially the surface expression of a structure, a fault, or fracture deep beneath the ground. Exploration utilizes free satellite images and digital elevation model (DM) data to map these linear and circular structures. What's amazing is that even ancient, deep-seated structures, some dating back to the Archean or Proterozoic, can be recognized in the modern landscape because they are immortal. Reactivated many times throughout geological history, VO. We use this analysis to find the space or volume necessary for a deposit to form. A successful exploration project needs space for the deposit to accumulate beneath the surface. And lineament analysis identifies where these volumetric spaces are most likely to exist. This method has been successfully tested for everything from oil and gas exploration, where it helps to find fracture collectors, to diamonds and gemstones like emeralds, where it helps locate the deep metal-carrying structures.
To confirm which lineaments represent potential openings, geologists employ sophisticated 3D strain and stress analysis, using both plastic and elastic modeling. In plastic deformation modeling, we use physical models made of mud and sand. We trace the main lineaments onto the model and then subject it to different types of simulated deformation, compression from various directions, or extension. After each deformation, we analyze the result. It is fascinating to see that no matter where the pressure comes from, there are always some faults that open our targets in red and others that remain closed, the blue areas. Since repeating this process takes time, sometimes having to physically rebuild the model, it is known as a relatively slow process. The elastic deformation modeling is a faster alternative, utilizing materials like gelatin jello. When the gelatin model, placed over a polarized light source, is subjected to deformation, the opening fractures cause a visible spectral diffraction of light, highlighting the highly strained or dilatant zones. By combining the results of the plastic and elastic modeling, we focus our efforts on areas that show the highest potential for opening under regional stress. This unique combination of techniques is so powerful that it can typically reduce the initial area of a mining license by 50% to 75% before expensive on-site activities begin. This means you can concentrate your exploration budget exactly where the big pot of potential resources is located.
So next time you hear about a new mineral discovery, remember that behind the big news is likely a structural geologist who carefully mapped the Earth's hidden architecture. It's not just luck. It's geometry, mechanics, and a deep understanding of how tectonic forces shape our world. If you are interested in these subjects, please subscribe, hit the like button, leave a comment, and share this channel with your friends. Until next time, keep exploring.
Welcome to my channel, where you'll find over 2,000 videos on geology, geochemistry, AI, and many other subjects. If you like what you see, help us grow by subscribing, liking, and sharing this channel.
I think these videos are brilliant, and I'm sure you will like them too. Please like, comment, and subscribe, and don't forget to click the notification bell.